In this section, we're going to look at the relationship between the three things we've been calculating in the last several chapters, specifically K, the equilibrium constant, delta G, the Gibbs free energy, and E cell, which we've been calculating in this chapter. And as you can see, there is a mathematical relationship between each of these different variables. Said another way, you can calculate delta G, K, and E cell for the reactions. And you can also predict the spontaneity. Remember that if E cell is positive, the reaction is occurring spontaneously. If delta G is negative, the reaction is occurring spontaneously. And if K is much greater than 1, then the reaction favors the products. So this is basically what we're going to do. Now, I will note, I took this picture right out of your textbook. We are going to use slightly different versions of these equations, especially this one, because this RT and F can be simplified, and then we use the log of K instead of the ln of K. I also want to let you know the new variable, which is F, Faraday's constant, which is 96,485 coulombs per mole. I also want to let you know that N is the number of electrons transferred, because that will come up. But note that RTF can be simplified because at standard conditions, we know the temperature, R is a constant, F is a constant, so we can simplify this, and then we just use the log instead of the ln. So the equations we're going to use, and we're going to do several examples as usual, are slightly different, but they're the same, they're just different forms of the same equation. So as I mentioned a second ago, if K is much greater than 1, and remember that K is products over reactants, that means we have much more products and much less reactants. Said another way, the forward reaction is favored. If delta G is negative, the forward reaction is spontaneous. If E cell is positive, the forward reaction is spontaneous. So all of these values are related to each other. So let's do two examples where we relate these two values. So it says, consider the following reactions. I'm going to switch over to the camera before I forget. It says, consider the following reactions. We calculate the standard potential for earlier. Calculated the standard potential for earlier. Calculate delta G and K for these reactions. How do the three values relate to the spontaneity of the reaction? So there's a couple of typos in here. All right, so we have Ag plus Pb yields Ag plus Pb2 plus. And I'm going to review how we calculate E cell for this one and the next one. And then we're going to use this reaction to do a couple other questions in a little while. So here we have Ag plus, which is going from plus 1, to Ags, which is 0. So here, plus 1 to 0 is gaining an electron. So this is the reduction reaction, or said another way, this is occurring at the cathode. Here we have Pb and Pb2 plus. Assuming that this reaction is hooked up in a galvanic cell, this would be the cathode. If it's just a general reaction, then we would not need to say that it's the cathode. All right, here we have Pb2 plus, which is going to be Pb, which is going to have an oxidation state of 0, and Pb2 plus, which is plus 2. So it goes from 0 to plus 2. It lost electrons. This is oxidation. And again, if it's hooked up in a galvanic cell, this is going to be the anode. So we can calculate the E cell of this, assuming it's hooked up in a galvanic cell. And that is E naught of the cell equals E naught of the reduction minus E naught of the oxidation. And if we look up the reduction potential of silver, okay, we find that it is 0.7996. And if we round that to 2 decimal places, we get 0.80 volts. And if we use the E of oxidation, we have lead. And if we find lead here, it's 0.126 volts. Or if we round it to 2 decimals, it's minus 0.13 volts. And when we do this, we find that the standard reduction potential of this reaction is 0.93 volts. So this gives us E cell. Now we have to calculate delta G and we have to calculate K. So for delta G naught equals minus NF E cell. All right, where N is the number of electrons transferred, in this case 2. 2 silvers gain 1 electron each, and lead lost 2 electrons to go from 0 to +2. So the number of electrons transferred is 2. F is Faraday's constant, 96,485 coulombs per mole. And E cell is what we just found. So let's plug in those values. Minus, it should be minus, 2 moles. All right, and this is an exact number, doesn't have sig figs, times Faraday's constant, 96,485 coulombs per mole, times E cell, which is 0.93 volts, and a volt is a joule per coulomb. When we do that work, we get minus 180,000 joules, or minus 180 kilojoules. And I'm using this as 2 sig figs because this is 2 sig figs, and you could argue this isn't perfect. The best way to write this, I should write 1.8 times 10 to the 2, negative 1.8 times 10 to the 2. But again, I don't want to get into sig figs too much here. So delta G is minus 180 kilojoules. We can also find K. And K is related to E cell in this way. E cell equals 0.0592 volts over N times the log of K. This is a slightly different equation than when it was presented on the previous slide. It's not actually a different equation, it's just a different form of the same equation. We basically simplified some constants. There were 3 constants in the previous one, and we basically simplified that in this way. So what we can find is that we know E cell, so we can plug that in. E cell is 0.93 volts, all right, equals 0.0592 volts divided by N, which is the 2 moles of electrons, times the log of K. Now we cross multiply, or we simply find this and divide this, and we find that log of K is equal to 31.4. Now we have to get rid of the log, so we have to take 10 to the log K equals 10 to the 31.4, and when we do that, we find that K equals 2.6 times 10 to the 31. So if we look at these 3 values, I don't know if I can get them all on the screen. I guess I can. So the E cell is 0.93, which tells us that this reaction is spontaneous because E cell is positive. Delta G is negative 180 kilojoules. That tells us this reaction is spontaneous because delta G is negative. And K is 2.6 times 10 to the 31, which tells us that this reaction is spontaneous in the forward direction because this is a large number, which means that the products are very strongly favored. So this number is much greater than 1, which means that the products are more favored than the reactants. Let's do one more example like this, and then we'll talk about why batteries die, which is the last section. So it says here, consider the following reactions, and we're going to use the standard reduction potentials, and we're going to find again E cell, we're going to find again delta G, and we're going to find again K. All right, so let's take a look here. Here we have hydrogen, which is going from 0 to plus. All right, so hydrogen has lost an electron. This is oxidation, or in a galvanic cell, this is what's occurring at the anode. All right, copper is going from +2 to 0, so it's +2, and over here it's 0, and this is reduction because it's gaining electrons, and this is what's occurring at the cathode, like so. Again, 2 moles of electrons are transferred. 2 hydrogens each lose 1 electron to form 2 H pluses, and copper 2 plus gains 2 electrons to form copper neutral. So 2 moles of electrons are transferred. I put here it's not always 2 because in both of these examples it was 2, but it isn't always 2. Okay, so now let's find E cell. So E cell, and we actually already did this, equals E of the reduction minus E of the oxidation. So we need to find the reduction potential of copper. And if we find copper on our list here, why am I not seeing it? It is 0.34 volts. So we plug that in, 0.34 volts. Now you could look up hydrogen, or you could just remember that hydrogen is 0. So E cell here equals 0.34 minus 0, which is of course 0.34 volts. We now want to convert this into a delta G, and we also want to convert it into a K. Well, delta G, from just like in the previous example, equals minus NF E cell. All right. In this case, we're transferring 2 moles electrons. F is Faraday's constant, 96,485 joules per coulomb, times E cell, which is 0.34 volts. All right. And what am I doing? The F is coulombs per mole, and the volts is joules per coulomb. And when I do that, I find that it's minus 66,000 joules, or minus 66 kilojoules. So E cell is positive, spontaneous. Delta G is negative, spontaneous. Finally, we need to find K. Well, in order to find K, we're going to use the same equation. E cell equals 0.0592 volts over N, the moles of electrons transferred, times the log of K. Well, we know E cell, it's 0.34 equals 0.0592 volts over 2 moles of electrons times the log of K. When we get rid of this and then divide, we find that the log of K equals 11.5. If we take 10 to the log and 10 to this, we find that K is equal to 3.1 times 10 to the 11. Okay, and this is usually a unitless number. Again, since K is a large number, much greater than 1, it means that the products are favored. So we have, again, consistent information on the direction of the reaction. The reaction is spontaneous in the forward direction because this is positive. It's spontaneous in the forward direction because this is negative. And K is a large number, so the products are much more favored than the reactants. The last thing that we want to look at here explains essentially why batteries die. And this is called the Nernst equation. And you'll notice that this is very similar to the equation we just used with the 0.0592 volts over N, and except this time we have log Q instead of log K. In this case, again, N is the number of moles of electrons that are transferred, and Q is current conditions, products over reactants, instead of K, which is equilibrium conditions. Note that when we're looking at this value here, what we're looking for is, just like we did with the delta G, a non-standard state. So the E cell, and then we're going to subtract out based on current conditions. As this reaction proceeds, essentially what's going to happen is we're going to start to subtract out more and more from the E cell. Said another way, the battery is going to lose voltage. And as you know from common experience, batteries will lose voltage until a point where they won't do what they're supposed to do anymore, right? So if you have a flashlight, it won't run forever on batteries, because as the chemicals get used up and the concentrations of those chemicals change, the voltage decreases and decreases and decreases. And when it decreases enough, it no longer functions properly. Now, there's other things going on here, and this is a little bit oversimplified, but I hope it gives you a general idea of what we're looking at here. Remember that standard conditions are basically having the solutions at 1 molar. But if you remember, the solutions are going to increase in concentration on the anode side as the metal becomes metal 2+ in the case of lead. It doesn't have to be 2+. And the concentration is going to decrease on the cathode side as in the case of the silver and lead electrode, the silver plus becomes silver. So the concentrations are going to change, and therefore the voltage is going to change, and we're going to look at these conditions in the terms of 2 examples. Switching back over to the camera here, sorry it's taking me so long. It says, consider when 0.1 molar silver plus ions are used at the cathode and 1.5 molar Pb2 plus ions are used at the anode. Find the potential under the non-standard conditions. So notice that at standard conditions, this is 1 molar and this is 1 molar. But if you let the battery go for a while, the concentration of the lead plus is going to decrease because some of that lead or silver plus is going to turn into silver. All right, the concentration of the lead is at 2+ is actually going to increase. And the reason for that is some of the lead is going to turn into lead 2+. Now, does this mean you necessarily started here with 1 molar? Probably not. And from the stoichiometry, you can tell that. That being said, it's just an example. So the Nernst equation, and the equation that we're going to use to solve this problem, is that E cell equals the standard E cell minus 0.0592 volts over N times the log of Q. So the standard cell potential, normally you would have to calculate, but we've actually already done this twice. So I've just showed the standard cell potential. We've already done this twice in 2 different examples. So what about Q? Well, Q equals products over reactants. In this case, it's the concentration of Pb2+. Notice we leave the silver out. Why? Because silver is solid. Over the concentration of, what am I doing? The concentration of Ag+, like so. So for Pb2+, in this case, it's 1.5 molar. And I forgot here, the Ag should be squared because there's 2 of them. And the Ag concentration is 0.10 squared. All right, like that. And when we do that, we find that Q in this particular case is equal to 150. So now we can plug this in. E cell equals the standard potential, 0.93 volts, minus 0.0592 volts, divided by still 2 moles of electrons transferred in this reaction. It's the same reaction we used earlier. And we're going to take the log of the 150. And when we do that, we find that E cell equals 0.87 volts. So you see, as the concentration of Ag plus decreases, which it will in a battery because it's going to form Ag, the effective voltage decreases. Now in this case, this may not be enough for the flashlight not to work. Okay, this may still be effective. Let's look at another case. Well, let's say now the concentration is 1 times 10 to the minus 4 molar. And I'm going to put 1.0 times 10 to the minus 4 molar for significant figure reasons. And the concentration of the lead is still 1.5 molar. Well, it's the same equation. The E cell equals the E naught of the cell, the standard, minus 0.0592, I forgot a 9, 592 volts over N times the log of Q. This time, Q equals concentration of Pb2 plus over concentration of Ag plus squared, which equals 1.5 divided by 1 times 10 to the minus 4 squared, and we find that Q is equal to 1.5 times 10 to the 8th. Okay, once we do that math. So now plugging in down here, the E cell equals the E naught of the cell, 0.93 volts, minus 0.0592 volts divided by the 2 moles of electrons transferred times the log of 1.5 times 10 to the 8th. And when we do that, we find that the E cell is equal to 0.69 volts. So when the concentration of the silver plus ions becomes 3 orders of magnitude or 1,000 times less than what it was before, the voltage now drops significantly down to 6.69 volts from 0.93. So when it dropped to 0.1 molar, it went from 0.93 volts to 0.87 volts. When it dropped down 1,000 times more to 1 times 10 to the minus 4 molar, it went down to 0.69 volts. So as you can see, the potential drops for the cell as the chemicals in the battery get used up. The last thing that I want to mention in this section is about actual batteries. And I'm not actually going to do the lecture on actual batteries because there are nice videos in the next section that are relatively short. Some of them have animations and they do a much better job than I'm going to do just talking in front of slides. So I'll allow you to watch those ones now that you have some idea of electrochemistry. But they do explain things like how a battery works, a car battery. So a car battery, I believe, is 12 volts. The reduction potentials that we have seen yet so far can't give you anywhere near 12 volts. If you remember, lithium is minus 3.04 volts and fluorine is 2.86 volts. So even if you have a battery with lithium and fluorine, it's only going to produce about a little under 6 volts. Well, how do we get a 12 volt battery? Well, it turns out multiple cells can allow that to happen. All right. They also talk about more of a standard type of battery, for example, this jelly roll battery. They also talk about a little bit about a lithium ion battery. So you can look at these different ways of that people are making batteries, and batteries are of course very important to us. So for the next section, there will not be a video from me. There are only some individual videos. I do want to let you know that I would never put on a test where you have to memorize different types of batteries and how they work. I do think though, with the practical nature of batteries, right, they're all around us and we use them every day, you know, and you have a little bit of an understanding of electrochemistry, it is worth 20 minutes of your time to put those two ideas together to try and understand how these different battery types are working. And as you can see, here's just 4 examples of different battery types. So that brings us to the end of the electrochemistry chapter. I know it's a lot of work. Some of the equations at the end are relatively straightforward, right? You're adding and subtracting things and doing some relatively okay algebra. But in the case of the balancing redox equations, that really takes some practice. So make sure you practice through that 6-step process and master it.